Now, in my case, I'm going to bypass the remote, right? I can just, that's fine. Okay. All right. Well, first, as my sponsor page from my lab indicates there, I don't have any money from the medical field at all. It's all defense money at this point. I'd like to see that possibly change, but just so you know, I don't build nanobots. I build macroscopic robots. So let's see if this gets us started. I want to tell you first that in light of the fact that I'm not across the road skiing at Mount Orford, I really do care about these topics profoundly. I have had many wonderful days of skiing at Mount Orford. I've been here a number of times, including some really remarkable powder skiing. So I do care. Just very quickly, I do have a laboratory. I've already alluded to that. You can visit the website and find out about many of the projects in it. You won't find nanobot projects there, as I say, but you will find a number of robotics projects. That's old. So today, as my abstract indicates, I'll be zeroing in on this claim, and although I won't be giving a careful argument, I will be giving an argument that at least perhaps has some bite for the claim that if you want to build nanobots, as I understand robots, as I understand nanobots, we'll be clear about that in a moment, you had better use formal logic to do that. And to the degree that that isn't being done, whether it's a macroscopic robot or a small, very small robot, I claim that's a very bad idea. In fact, I will be politically incorrect and take out the perhaps and say that this is just outright true. I have two claims to make. First, that if you want to engineer nanobots relative to their programs, which are known to be correct in advance, you should use logic. And if you want to make sure that nanobots don't misbehave from an ethical standpoint, you should also use formal logic. So we'll look at this one here first. Now again, you have to buy into my basic scheme for what a robot is. This is taken from the by far dominant textbook in the world of artificial intelligence, AIMA 2E as it's known. It shows that an agent has this structure. You have to perceive things from the environment and then take actions. The question is, what's sort of on the inside here? What's the program that dictates how the function from percepts, as they're called, to actions works? And my claim is that unless, again, you use logic, there's going to be a problem. Now, if you're building nanotechnology in any form that does not conform to this basic structure, what I'm going to say is not going to apply, although I would then want to know why you're not thinking about it in terms of this structure. A vaccine, well, maybe it doesn't abide by this, but an actual robot or a swarm of robots designed to go into your body and do things, there, to my knowledge, in terms of intelligent robots, is no other basic scheme, and it's generally not in any way rejected. Now, a little bit more carefully, what would logic-based robotics be? It would be the field devoted to building robots whose actions are a function of what the robots know and what they believe, where the program in question computes by carrying out a form of reasoning. Generally deduction, although it need not be deduction, a search for a proof, finding a proof, and the proof says you ought to take this particular action. There are lots of examples from my own life where this technique has been used. I'm going to run through these very quickly. Again, these are confessedly macroscopic. But we've done things that people have said would be impossible in terms of speed. We've built robots that navigate ever more complicated versions of the Wumpus world, which is a famous testbed in AI. So there's a grid environment, and it gets larger and larger and larger. And we've shown that using formal logic, computational logic, has managed to handle this in a way that allows us to predict perfectly that the robot is going to behave as advertised. It isn't just that it's another way of doing it. It's that in our case, we know exactly what the robot's going to do. And we know we can prove ahead of time what the robot is going to do. I won't bore you with this particular video, but we've got a number of them. I've also done work in the area of getting a machine to demonstrate its intelligence by navigating human-level IQ tests, where, again, we're only using formal logic to do this. This is the this is from the Wechsler adult IQ test. Probably a number of you in here took this block design problem when you were younger. As a matter of fact, I did. There's a goal state. There's a set of inputs. Those cubes can either be white on one side, red on one side, or red and white, and you have to reach the goal state. And here's Perry doing this by using logic. Again, I admit these are macroscopic examples. We've also worked on the false belief task extensively with support from IBM, and continue to work on this if you're not familiar with the false belief task. In this case, the little blonde-haired kid in the middle is the, quote, robot or softbot in Second Life, and he's going to be confronted with the challenge of, and again, I will not run through the whole video, the challenge of trying to figure out that if the teddy bear is placed in container A, and then a bystander who sees where it's placed leaves, and then someone comes along and moves the teddy bear from A to B, and then this person comes back, the child has to be smart enough to realize that the person who left will look for it where it was originally placed. The media has recently completely bowdlerized this R&D, but that's okay. Still, the basic point, and I'm going to skip this, is that we have a general cognitive calculus that is based in mathematical logic for how to do this in the general case, and do it very, very quickly. All of the things I'm mentioning here, by the way, are described in publications, which if you're interested, I'd be more than happy to direct you to them. But in this case, what we're able to do is show that no matter how large the problem gets in the false belief task, we can solve it rather quickly with full generality, and that's because and this would apply to nanobots, we're not saying, and I'm not saying here that a nanobot has to laboriously go through an object-level proof to figure out whether it should carry out some action within your body, but rather that being done in advance should allow you to provide what's generally called a tactic or a method, which can then be fired. And you still get the advantages of knowing ahead of time that the robot's going to behave as you want it to. There's still a proof in the background, but it's generated very, very quickly. We've also done work on the wise man puzzle. Up until the time we did this work, it was thought that this would not be tractable. So that's one of the major objections that people have to this idea that you would use these kind of logic-based techniques for very small machines having to operate at a very high rate of speed. In the wise man test, a king confronts three wise men with a very difficult problem. He has 5 hats, and 3 of them are white and 2 of them are red, and he tells them he's going to call them fezzes on their heads, but they're not allowed to know what's on their head. They can only see the fez on each other's heads. And in fact, what he does is he puts 3 white hats on the wise men. And wise man A says, look, I don't know what color my hat is. Wise man 2 says, I don't know either. Wise man 3, being really smart. By the way, this test has been given ad nauseum to human beings. Only about 1% of the adult population, unfortunately, is able to solve it. But there is that 1% that solves it reliably and provides a justification. The third wise man says, well, I know I have a white hat on my head, because the first 2 wise men were not too smart. They opened their mouths, and they probably should have kept them shut. The basic structure of this argument is fairly simple. When the first wise man says, I don't know whether I have a white spot, that allows the third wise man to cross out the possibility that, knowing that the first wise man would use the process of elimination, that there's no spot on either of the other 2, because if the first wise man had looked over and seen no spot or no white hat on the heads of the other 2, he would immediately have proclaimed, look, I know I have a white hat. So if he'd seen a red hat on the other 2, that's what he would have said. Then when the second wise man opens his mouth, that allows the third wise man to rule out another possibility, leaving the final possibility as either what you're seeing there in the third row of the other 2 possibilities, that there has to be a spot or a hat on wise man 3's head. Now, rendering this in mathematical form and showing that it doesn't matter how many hats you're talking about, but that formal logic in this day and age, in 2008, given the speed of automated theorem-proving technology, was a non-trivial affair, but we did show that. And there is a paper on this. Again, this is a far cry from what a nanobot would have to do, but we know that speed is increasingly becoming a non-issue, and that we have absolute certainty as to what the robots are going to do. We've also showed using some discussions at breakfast about all the robots in my laboratory, ranging from highly simple robots that even clever high school students can use. We've shown that using formal logic and allowing the compilation of online methods, even painfully simple robots, can solve the wise men task. In this case, the black represents the red hat and the white hat. So you can see they all have black hats, so to speak. These are dirt simple robots, but they are able to solve the wise man puzzle. And this had not been done before, even though it looks unassuming. So those are just some examples, but returning to the first claim, I can actually prove that to you if you buy into the scheme of what an agent is and what a robot is. It's really a very simple proof. The behavior of a nanobot is known to be correct only if the behavior of the agent function that governs that robot is known to be correct. An agent function is known to be correct only if the program that computes that function is known to be correct. And then the third premise, the program, and I'm giving these things proper names there, but they're arbitrary names, is known to be correct only if the engineering of that program is based on formal logic. The third premise is true because in computer science, this is just an absolute brute fact. There is no other way to do program verification than to use formal logic. There literally is no other way. The reason for that is because the only way to know things for sure is to prove things, and the only way to prove things is to use logic. Two applications of hypothetical syllogism allow you to infer the conclusion, which is the first of my two claims, namely that the behavior of a nanobot, an arbitrary nanobot R, is known to be correct only if the engineering of this program is based on formal logic. Now, we can take risks, and I suppose that's part of the very nature of medical research, but from the standpoint of the formal sciences, there's a clash not of civilizations but of paradigms here, and I will leave it to you to help me sort this out. The second claim is the only way to handle the ethical issue is to use formal logic. Now, here I draw upon a famous paper by Bill Joy, which was in fact catalyzed by Ray Kurzweil, arguably the most, I don't think arguably, I think as a matter of fact, the most read paper on the internet, Why the Future Doesn't Need Us, in which Joy advances this thesis, and I directly quote, in the relatively near future, and now I will just summarize, we're basically toast. We will all fade away and become extinct as a race. He gives three arguments for this claim. The first argument is to reiterate the Unabomber's argument, and that, ladies and gentlemen, from the standpoint of formal logic, is a horrible argument. I'm not going to go through it, but we're just going to say goodbye to it. I will say that one of my problems with the argument is that it does assume that robots in the future and AIs in the future will have absolute autonomy. But from the standpoint of AI and computer science, nobody has a formal definition of autonomy. And to the degree that we understand what it is, we know that it is ridiculously hard to get a robot to take just one action that is taken autonomously on the basis of what you might call free will. And I've played around with this. I don't have any support for this work, but I've tried to use sort of everything in the AI literature that pertains to total and complete autonomy to get Perry to take one free action. And from the engineering standpoint, we really have no clue how to do this. So the Unabomber argument, I don't worry about too much because I really don't see this future coming. I don't even see the start of a definition for what robotic freedom would be. Argument 3, I'm skipping over 2 because it's much more relevant to us at this conference. Argument 3 is this idea that we will download ourselves into robotic hardware as it gets more and more sophisticated. This relates to the human body 2.0 to some degree. This argument has a major problem, so I'm going to throw it away as well. The problem number one is that it's an enthymeme. It isn't a formally valid argument. You do have to add a premise. And if you set it out like this, you can in fact conclude in step 4 there that the black future that Joy says awaits us does await us. But the problem is that it assumes that speed is all there is. And this is the same thing that Kurzweil does repeatedly. Kind of runs afoul of the basic mathematics behind computer science. Speed is not the issue. What's the issue? The issue is, finding the function that computes whatever it is you're interested in doing. We know, and I've got lots of papers on this, I'm not going to bore you, you'll find lots of them on my website, but here again is the problem. We've known from the dawn of AI that speed is not the issue. Moore's law is wonderful, but the problem is finding out what the functions are. Now I'm not going to go through this, there's a body of mathematics that underlies computer science. It is, by the way, all based in formal logic that shows us there is a limit beyond which conventional machines, computing machines, cannot pass. Many of the problems that humans confront require at least taking a stab in this direction. The problem is finding a way to, that's the so-called pi 2 level in the arithmetic hierarchy, generally required, at least in some cases, that humans be able to process information at this level when they try to program. So when you try to write computer programs, you're doing something that's quite remarkable from a mathematical point of view. Speed is a complete non-issue. That is not going to help you with these problems. It's a matter of the ingenuity in finding the functions. Now, the argument that has more relevance for us here at this conference is argument 2 in this famous paper. And this is a direct quote. You'll see that nanobots and nanotechnology is specifically called out. Robots, engineered organisms, and nanobots share a dangerous amplifying factor. They can self-replicate. Now, I'm not entirely sure what the idea here is, but I think it has something to do with the fact, or at least the claim that, if you put together nanotechnology with replication, or nanobots with replication, that the danger is that these nanorobots will just get out of control and self-replicate in your body. It's a more general version of the concern that I have about controlling robots, but it's something that pertains specifically to self-replication, and I don't fully understand where joy is coming from. But anyway, that's the concern. What I do know is that, again, the antidote to this comes in the form of a particular methodology for designing robots. And I'll go through the steps for you. If you're worried about a robot violating your ethical code, whatever it is, you have to first select that code, of course, to make sure that the robot is not going to abrogate it. Now, I don't know what that ethical code would be, but generally speaking, killing an innocent person just because you want to self-replicate in a body would be a bad idea, I think, according to most ethical codes. But whatever the code is, you have to get it. You have to then represent it very carefully. There is a subfield of logic devoted to this. It's called deontic logic. I, of course, admit it's not exactly a popular field, but a whole group of logicians devote most of their time to figuring out how to take ethics and make ethics very precise. So you have to represent your ethical code in deontic logic. You then have to computationalize that or mechanize it, and then put it on the robot so that every action to be performed by the robot can be proved ahead of time to be morally permissible relative to that code. And also you would like every obligatory action for that robot to be in fact performed. This approach is one that I have laid out in connection with a medical example in a hospital involving 2 robots in an IEEE piece, which I invite you to, and it's not that technical, and I invite you to take a look at that. It is on my website in my hot-linked Vita. So what I really should have done was used an example from nanotechnology, but I just don't know enough yet about how these robots are being designed. Maybe that's next, and we'll work on some of those examples. So again, these are my 2 claims. And you may reject them, you may not want to hear about them, but they apply, I submit, and I truly mean this, they apply to whether you're talking about an unmanned aerial vehicle with offensive capability, where the mission is critical. They apply to trying to travel to Mars and leaving a robot or an immobot in control of the spaceship. But they also are going to apply to robots that are very, very small and trying to do things that are very helpful in your body, mine, and the bodies of other human beings. Thank you very much.